Hello everyone. Today I'm going to be presenting General Relativity with the headlights on, video number 3. And in this presentation we're going to be developing the pieces for the next presentation where we'll put the pieces together and get Einstein's stress energy field equation using our simple methods in which I'll be using mostly images to communicate, and we will be restricting ourselves to just basic arithmetic, what I call hardware store arithmetic, and I'm purposefully limiting myself to being able to use only the arithmetic operations, plus and minus, multiplication and division. Now last time I had presented a puzzle for the viewers and left it for them to solve it if they so chose. And so I feel it's only fair this time to show a solution for that. And a very simple, nice, I think you'll like it. It might look a little tricky at first, but when you see what I'm doing, actually, it's astonishingly simple. So I'm going to here introduce the tools to be able to approach this as I did last time, but a reminder. And similar triangles. We're going to be using similar triangles. Now, a similar triangle is a series of triangles that have a right angle on one side, and or what I like to call 1/4 full turn. When you have that, and you have the far angle opposite the quarter turn be equal in all the triangles, then the triangles are similar. And what happens that's so incredibly useful for these types of triangles, the similar triangles, is that the ratio of the sides for all of the triangles, small, large, intermediate, they all have the same ratio of the sides. So if you're looking to solve something to do with ratios, and you can compare two similar triangles where you know one and you want to find out what the other one is, that becomes very easy to do. And you don't have to go through a complex analytical derivation and sometimes get fancy. We don't want to do that. So I'm going to be using what I presented in more detail in the last presentation, number 2. But basically, I've thrown again two vectors, momentum vectors, this one along H and the one along, which is a green line, and the one along O, which is the red line. And when the observer, which might actually be a piece of equipment or a person, moving along what is the timeline, H, the green arrow there, and they come to B and they look over at the momentum line of this other person, the red line, they see that the distance is along B and G. Now B and G just has to intersect the red arrow at a quarter turn. That's the only place where the quantum mechanical waves sum up. It's also the closest distance in space-time, and that has to do with allowing the quantum waves of matter to sum up, and means you can actually take a measurement there, which means that the line B to G is actually the line of simultaneity for the person riding along H. And as I discussed last time, that is not the same line of simultaneity for the person riding along the red line, O. So if you want to see that again, go back and look at it. So here I'm going to show you next the chart that we had last time, and I'm going to show how to use similar triangles to solve the Lorentz transformations. And we're not going to do any fancy math here. So there's on the right hand side, the diagram we derived last time, and in the lower middle we have the 4 expressions for the Lorentz transform, and the first one there is highlighted in yellow. We're going to do that first, and I'm showing here how what I've done is I've taken that triangle before that's the triangle H, line H, A, and O, the green, blue, and red there, and I've pulled it out. So we can use that as reference, because what we really want to do in the Lorentz transformation, so you can see that ratio H over O, well that's the ratio H over O corresponding to that little red triangle that I pulled out along, see the arrows, I pulled it out and put it on the top there. So we're going to look to see if we can extract another triangle inside this construction here, and then determine the Lorentz transformation from that. And I'm going to show you next. I'm going to go down. I like doing this with the toggle, but it can screw up sometimes. Let's see if I can do it. Okay, down, up, down, up, down, up. Do you see how what triangle I'm pulling out of? By doing that, you should be able to see that this triangle, how would you call it, with the green, blue, and the red and orange line there. The one on the right hand side, that one corresponds to, and I'm going to go back up to that triangle on the top there, and you can see it if I toggle. Hope it comes through for you. So now we look over, and I've also, you can see how I've twisted around our little reference triangle, rotated it around. See how I've rotated that? The red line starts out on the left-hand side of the right-hand side of the triangle on line O, and then look, O is kind of more on the bottom but on an angle. So when you see it done that, rotated, you can see, oh, it's a similar triangle, which means that I can read H over O. I can see that H over O, like if you look at this first expression I put and again highlighted, the one on the top, H over O corresponds to D over this T times V plus that length D, the orange little d. So, and then I've got the D and then divided by D plus T over little red T times V. I want to take that over to the other side, so I multiply both sides by D plus T, little red t, times V, multiply both sides by that. And what you get is D equals D plus T times V times 8 over O. That's the first expression of the Lorentz transformation, just like that. So let's do the next one now. So we did the first one, see that D, read it off. Now we're on to the next one, which I've highlighted in yellow again, and we're wondering, what triangle in this construct over here on the right can I pull out and solve the next equation of the Lorentz transformation? So again, I'm going to show you which triangle I pulled out, and I'm going to toggle it. Can you see which one I pulled out? See on put your eyes on the right-hand side construction there, and the triangle that has D times V on the bottom, the blue line there, and it's got the green line T that's at full length, and it goes up to that event E. They call it E because it's an event, like maybe a little explosion or a light flashing or something on this space-time diagram. Now, so again, it's that triangle on the far right-hand side there. Now let's just see if you can see that. See how it goes in and out, in and out. Okay, so now let's look at this, and see how I rotated the triangle O, H A O, or what are we gonna? Let's pick something neat. I can call that triangle because it's kind of like a triangle that you used to get ha, ha, right? Well, OHA, the triangle ha. Anyhow, so we're going to use that, and you can see how I rotated it, and it's also a similar triangle. Well, you can see how it's similar with the triangle that I extracted. Now let's see what that tells us, because we're looking for H over O, and the line T, T over this T plus D times V is the same ratio. If you take t and divide it by t plus d times v, is the same ratio as h over o. So I write that down: t divided by little red t plus d times v uh, equals h over o. So that's that highlighted expression on the top one, and then I take the d plus t, the little t, red t, plus d times v, and I multiply both sides by that. So I isolate the big green t on the left-hand side, and I get it over on the other side, and then I get the expression t, the big green t, which is, by the way, the capital expressions refer to the original green vector, the observer on that line, and the small letters like small red t, small orange d, etc. They refer to the measurements that the guy on the green vector would measure while taking observations of the guy in the red vector moving away from him. And so I'll say a bit more about that later. So we still have, where are we at? We've solved the second expression. So I'm going to move this whole thing up. Then I'm going to solve the third expression. So here we have the third expression highlighted in yellow. Now we look at that, we go, what similar triangle we're going to pull out of this space-time construction on the right-hand side in order to solve the Lorentz transformation for this. So I go down. Now, can you see which one I've pulled out? I'm going to toggle it for a little bit longer this time. Can you see which one that is? Okay, so I'm going to go back. No, up. There we go. I almost messed up the toggle. Anyhow, so it's this one. We got the event E, that star there, the black star on the upper right-hand side, E, and that triangle underneath it was the small red T, and that dotted orange line over to the intermediary point on that line T, and going up to E again. So that's the triangle we pulled out, and you can see how I rotated the reference triangle there, so that A, which is on the top, is actually on the bottom now and upside down because I kind of flipped it. So so now we want h over o again. So h over o. Well, h corresponds to this one, small t, and o corresponds to the big T minus big D, the blue one, blue D, times v. You can read it off of the triangle there. So I write that down. Small red t divided by t minus d, all big green t minus blue big D times v is equal to h over o. So right, and then I multiply both sides by what's in brackets there, the green big T minus blue big D times v. I multiply on both sides, so isolating the t, the little red t. Small red t is equal to big green T minus big blue D times v times h over o. So there we have it again. And that's the third expression. Now we're gonna do, and we're almost done. We got the last one. It's a piece of cake. Take a deep breath, relax. I hope if you're not tired, you must be getting, really quick on this. If you are, well, we can rest a little bit. I have a breather right now. So let's look at this. And the question again, what triangle can we pull out of this space-time construct in order to solve this last expression of the Lorentz transform? So I'm going to show you what one I pulled out there. See, can you see that? So I'm going to toggle up, toggle down, toggle up, toggle down, toggle up, and see how. Okay, so you can see it's this one. Let's look at the event here with the black star, and it's the triangle right beside it, the one with the red D inside there, for that the orange line on the bottom. So I'm going to toggle it up and down a few more times so you can see. So we're doing the last one. I got messed up on the toggle again. That happens. So, whoops. Toggle is over time. We really get messed up. So here we go. So it's this this one on the top. Oh, so I wanted to go up. It's this one here on the top right hand side triangle one. So and now let's solve it. So I take what we want is h over O, and we see that h corresponds to d, the small orange d, and O corresponds to the big blue d minus the big green t times v, the one on the top there. So, and we want h over O, so I write down the expression, little orange d divided by the big blue d minus the big green t times v is equal to h over O. So that's the last expression. And there we go. So here we have, we've derived all of the expressions for the Lorentz transformation. Now you might want to check up on me because it's good. Good to see that little mistakes haven't crept in, and you'll need to. Traditionally, the original Lorentz transformations following Einstein. Einstein had for the green vector, he used the unprimed coordinates, and prime means you put a little like a single, like a quote, but only with one, and so that doesn't have those quotes. And on the primed coordinates, which means, well, those ones, they put that little tick on the top. And those will show up in most accounts of the Lorentz transformations. So, and that refers to what the green guy riding on the green arrow will see looking at and observing on the guy riding on the red arrow in terms of time and space and all that sort of thing. So, so you can see which expressions that I have, because I have the small cap, like the little red t and the little red d. I use those instead of the prime. So those equations with my small t and small d on the left-hand side will correspond to the expressions with the prime. So that'll help you check up on me. Otherwise, you wouldn't know which is which. So let's see, look more. So here I'm saying, just talking, getting ready for the next derivations here. So reminding you that gravity is a weak force, and that for small masses, which will make the gravity weak, and low relative speeds, we would expect when we get the new expressions, the Einstein type expressions, they have to match the Newtonian expressions for weak forces like small masses and low relative speeds. So that provides a good check, because at the low mass and low relative speed, weak forces, low speeds, the Newtonian expressions should match the Einsteinian expressions. So it's for at least for mass, that turns out to be true. So I'm going to start with the Newtonian expression and build on that, expand it. So when we drop a stone near the Earth's surface, now notice it's a stone, it's small mass, and gravity is a weak force. So Newtonian expression is going to be pretty good for that. And so we get the we get from the Newtonian expression, force equals the mass times acceleration, and it equals m of the stone, the mass of the stone, times the mass of the Earth, times the gravitational constant over r squared. And that's the Newtonian expression for gravity. And then I just take I cancel out between the m stone I cancel out to get A on one side, and I cancel the m stone from the um, m stone times mass Earth times u2. And what I get is the expression on the right-hand side there, that the acceleration is equal to the mass of the Earth times gravity divided by r squared. Now, the total acceleration just for mass, total acceleration for just mass, so we're talking about mass, not light, for example, is obtained by multiplying the total surface area of the Earth, where you have all those forces all the way around the Earth in every direction, so over the total area. So you multiply 4 pi r squared, and down in the bottom here, times the acceleration, equals 4 pi r squared times the mass of the Earth times the gravitational g divided by r squared. So we get the expression for the total acceleration, which is for mass. It applies mass only. It applies to also the Einstein equation. But the Einstein equation we'll talk next. Time for some fun. Let's calculate the curvature of a sphere using parallel transport. So I'm going to try something which it's kind of tricky actually. It's like, you know how you try when you're clipping some hair out of your ears with the scissors and you try not to cut your earlobe off? It's one of those things. So I'm going to show here, you've got the diagram as well to help, but I want to do it with my fingers. So my index finger represents an arrow lying on the equator pointing to the North Pole. And then I go up, following parallel to the Earth's surface the whole way, and I get up to the North Pole. And then I go down, 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 down on the other side. And my finger's on the equator again, but it's pointing down now, straight down rather than straight up. And then I go around the circumference of the equator to where I started, and my arrow is still pointing down. So it started out going up, and then went around, and then down, 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 and then around, and it ends up reversing its direction. You know, when you hear somebody say, "Oh, I was out, hit some black ice," I remember. Well, you don't know this yet, but I'm originally from Canada. Hit some black ice, and I did a 180 on the highway. So we know what that is, complete reversal. And it just so happens that when you want to talk in terms that are self-referential, like you don't want to use degrees. What's a degree? It's a month, and what's a month? 30 days. And, you know, it's arbitrary. But a pi radians is... it's a ratio pi to comparing the radius, which is a geometric thing compared using a geometric thing. So it's not arbitrary. So they use radians. Now, 180 degrees is equal to pi radians. So this arrow, I'm not going to try that again. This arrow does a complete 180, which is pi radians. And the way to calculate the curvature of a surface is you take the area enclosed by the perimeter of your journey, and I'll go to the chart now. It starts at position 1, goes parallel to the Earth's surface again up to the North Pole, and then goes down, down, down the other side, so that's at 2, goes down the other side to 3, where it's pointing down like I showed you with my finger, and it goes round, 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 and back, still pointing down. So that transit is 1/4 of the surface of that sphere. Now, the sphere surface is 4 pi r squared, and you divide that by 4, you get pi r squared. And then, so it turns out that the method of calculating curvature is to take the change in the angle and divide by the area enclosed by the perimeter of your journey. So that works out to the change in the angle is 180, so it's pi, and the area enclosed by that perimeter of travel is 1/4 of the surface. There's 2 of those surfaces on the top, 2 on the bottom, so it's 1/4 of the surface of a sphere. So it's 4 pi r squared, the surface of a sphere. 1/4 of that is pi r squared. So you take the change in the angle pi and you divide by the area enclosed by that transit, which is pi r squared, and you get 1 over r squared. Now, that's good to know. First of all, you're seeing that curvature is expressed in terms of the radius of arc, the radius in the arc. And the other beautiful thing is 1 over r squared. We know that the units, I'm always checking units, very important. The units are 1 over r squared, which is meters squared. So it's 1 over meters squared. So we're going to need that. And we'll come back to this again, have even more fun. But right now, I want to do a complete derivation of this expression. You see it at the top there. That the curvature divided by the mass density is equal to 8 pi g, which is Newton's gravitational constant, divided by c squared. Now, this turns out to be, like they call this, Einstein called it the Albert constant because he invented it. People called it the Einstein constant because they don't want to get that chummy with the guy. So it's known as the Einstein constant. It's just a constant k, like any other thing. But it turns out that this constant tells you almost the whole story about relativity. So we need to look into this thing. Yeah, and I got some really cool stuff to say about it. But first, let's go through and derive it. So we start out with, Newton's expression for gravity is the force is equal to m1, m2, the two masses times g divided by r squared. M1, m2, g divided by r squared. So I want to get at the acceleration because we're talking curvature, so we need to talk the acceleration. So I divide out that first m, which might be the mass of a stone, and I leave the mass of the Earth in there. So we get force divided by mass is equal to acceleration, and that's equal to the Newton's gravity constant times the mass of the Earth in this case, divided by the radius of the Earth squared. Okay. So now we have an equation that we're used to. We know it's true, and it's true for the way it's written right there. It's just true. And look, I just looked at it to make sure that it was the version I thought of it. So it's another truth, and this is the algebra. Which meant in Arabic, what you put on one side, you got to put on the other side. So we're multiplying in this case both sides by 8 pi r squared divided by c squared divided by the initial volume, VI. And I put the little I in there also to distinguish it from velocity. So when you see the little VI, initial volume. So, and we don't even have to worry about why it's 8 pi r squared, but I already told you that light travels twice it goes through the curvature of space, it goes through the curvature of time, whereas a rock only goes through the curvature of time because the rock is mass. So light gets twice the curvature, so you go from 4 pi r squared, the surface, to 8 pi r squared. You got to put a 2 in there. So, but I didn't have to tell you that, but I did anyway. So you multiply both sides of the expression above, which we know is true, by 8 pi r squared divided by c squared divided by the initial volume. And we get the next expression. Now, you notice on the, I have multiplied by r squared on the left here, 8 pi r squared divided by 8, so and so. And we started out with an r squared on the bottom, so there's 2 r squareds, one on the top and one on the bottom. We can cancel that sucker, so that's the next step. Cancel the r squareds on the left. And you haven't changed the equation, so it's still true. Then we do something really easy. We multiply both sides by the mass of the Earth. And on the left-hand side, then the mass of the Earth disappears, it cancels. And it shows up on the bottom of the, on the right-hand side. And it shows up on the bottom of the left-hand side because there's no mass there before and now there is, so nothing to cancel. Then we multiply both sides by the initial volume. I notice it's got big here. I gotta shrink that little sucker. Ooh, there we go. Save it. Great. So then multiply both sides by v, and what you get, I got to shrink this little sucker. Sorry, this is a little bit nutty, but gives you a chance to look at the diagram more. It's probably good. I used to love when professors used to do that. They woke me up. What's going on here? So what I just did is I multiplied both sides by the initial volume. And now I've isolated on the right-hand side 8 pi divided by c squared times g. So it's 8 pi g divided by c squared. That's what we're looking for. You see on the top there, we got the right-hand side. And on the left-hand side, we have the expression, which is 4 pi r squared times 2. I should just, yeah, I can change that to 8. I'm going to do some changes here. Upgrade on the fly. Get rid of that 2. Delete 2. Wait, there we go. So 8 pi r squared, and that's the curvature, total curvature, divided by c squared, divided by the initial volume. Now, when you check the units of that, you indeed get 1 over meter squared. So the units tells you that that is a curvature. And so there you have it. So what we've proven there is that the curvature divided by the mass density is equal to 8 pi g over c squared. And if you work out the units, it's meters per kilogram. Now, it's really cool. I'm going to show you one application before in that ugly brown thing. Move it up a bit. So if you take c squared divided by 8 pi g, like you invert it, and then multiply it by the mass density, you get 1 over meters squared. And this is is curvature. So if you can, now, this is so great that I have to pause, let it sink in. You start out with a mass density. And we can look. We see, oh, I've got the moon there, we've got the Earth here. You know, those are the only two big weights and mass densities in our vicinity of the universe, and the moon is not doing too much if you're close to the Earth. So it's basically just the Earth. And you take that sucker, the Earth, and you multiply by c squared divided by 8 pi g. That's the inverse of that thing above. And multiply that by the mass density, you end up with getting 1 over meter squared, which is the curvature. The curvature that the mass density of the Earth imposes on the nearby space-time. Now, okay, so I'm actually going to calculate that for you with us, and that's even more fun to look forward to. Now, this thing I'm going to show you now kind of drove me nuts at the beginning. So, but I've spent the time to make it really, really clear. And it actually, I think it's very, very important. So at the top there, you say, see below, and you have here 2 copies of the same expression. And inside, I have the same terms exactly, okay? And it's in the same units. So you'd think it's only one, you know, it's the same thing twice. And why are you even showing it? Okay. Well, it turns out if you make a slight difference in the way you group the existing components there, just group them. You're not changing anything. Didn't multiply by anything. Didn't divide by anything. You just associated them differently. You group the components in 2 slightly different ways and get 2 different interpretations of the same thing, and which turns out to be important. So I'm taking, let's look at the first one here, the one on the left. And it says 8 pi r squared times a over c squared times vi, and divided by the mass density is equal to 8 pi g over c squared. So now, this says on the blue, inside the blue circle there is curvature, and we can see on the inside the yellow oval curve, is the mass 1 over the mass density. Okay, so we have the curvature divided by the mass density, that's what the left-hand side of that expression is equal to 8 pi g over c squared. Yeah, well, we just calculated it before. What's the big deal? Well, watch this. If I just, on the same expression now, on the right-hand side, if I group it and I take 8 pi r squared a, same thing, divide by the initial volume, but I kicked the c squared out, don't want it this time. And so the c squared gets grouped with the mass density, me over the volume, as shown in that green, what do you call that, polygon or something. Yeah, it's shown within that green polygon, c squared times the mass of the Earth divided by the initial volume. What it says is that, and then on the top, I grouped them, 8 pi r squared a over the initial volume in the red polygon thing. And that red polygon kind of looks like you remember I did that thing with my finger? That was not intentional. So what you get is, with the expression on the right, is the strain acceleration divided by the energy density. Now, earlier on, we calculated and figured out that the energy density is a stress. So what we see here is that the strain acceleration divided by the energy density, which is a stress, so strain acceleration divided by stress is equal to 8 pi g over c squared. And the units are still mass divided by kilogram. So what this expression on the right, just by grouping it differently, you have the strain acceleration divided by the stress. So you have that expression in terms of stress and strain. Now, I've talked stress and strain earlier, okay? But if you group it the same thing in a slightly different way as you did on the left, you have the curvature divided by the mass density. And, you know, it sounds like a different animal. But what's so important is to be bilingual in this respect, because it's not the same animal. This is the same darn thing. And it's telling us, if you want to talk stress and strain, go ahead. We got the expressions. Let's move that c over, c squared rather, move it over. If you want to talk curvature divided by mass density, then group the c, leave the c there and group it in that blue little circle. And you get curvature divided by mass density is equal to 8 pi g over c squared. So this tells us that when Einstein's stress tensor, you know, is they call it the stress strain energy tensor expression, that's on the bottom. You got energy density and strain. But if you want to just keep that c squared group in that blue circle there, then you can talk curvature and mass density. So, and by using that expression 8 pi g over c squared, you can change one side of the equation, which is talking stress, and you can change it into the other side of the question, talking curvature. So this is like the universal translator. This is like the Rosetta Stone. You might want to do a screen save or come back and ponder this a little bit, because it opens up. It's a simple thing. It's Einstein's constant, K. Done with it, right? Memorize it or whatever. No. This thing is almost the whole story. Just this one little thing. Blow that constant up. Understand its nuances here. So it's very exciting. So what do we got next to talk about? Okay, so, we're gonna actually calculate the second. I don't like saying, 8 pi g over c squared, constant, put the constants, look them up, put them in there, get the answer. No. Now, what I'm gonna do here, I'm gonna do it using parameters that are applicable to the Earth and measurable on the Earth, which we already did it. We derived the whole thing, the curvature expression. Let me go back and see if I can do that. Yeah, here we go. Complete derivation of the curvature divided by the mass density equals blah. And I derived that using the stuff of the Earth. you know, 8 pi r squared, that's the Earth. Volume of the Earth, the acceleration on the Earth you can measure. So the radius you can measure. So, and the mass of the Earth you can measure. So you don't have to talk about Newton's constant or other things. You can just go and measure it on your planet. Or if you're in the moon, use the moon's values and you'll get the same constant, which we're going to calculate that next. So I have to go back where I was, which was here. And we're going to calculate that constant. So the expression to use with the mass density of the Earth, okay, 8 pi g over c squared. So let's calculate it. Curvature divided by mass density for the Earth and see if it matches what we predict to be 8 pi g over c squared. So here we have in brown, getting towards the middle here. Radius of the Earth squared equals 4.05, etc., times 10 to the 13 meters squared is the units. The mass of the Earth is 5.9722 times 10 to the 24 kilograms. Oh, I was wondering where that big amount was. 10 to the 24, huge mass. Okay, c squared is equal to 8 point. This is, remember, it's not just c, which is 300 million meters per second. This is c squared, so it's 8.987, etc., times 10 to the 16. Okay, so, okay, and we're going to use the acceleration as the mass detector. We're going to use an ordinary stone, and we measured that as 9.81, give or take, meters per second squared. So we plugged those values into an expression that we used earlier. And then I actually showed you what I extracted when I put it into Excel, the actual numbers. And what I get is the result, which is 8 pi g over c squared is 1.86378 times 10 to the minus 6 meters per kilogram. 10 times 10 to the minus 26. Now, you look it up on the internet, you find that that's true. And you can take the 8 pi g, you know what pi is, you know what g is, you can look it up. You can look up c to the c and do c to the fourth, or c squared, whatever you want. I mean, yeah, it's the same thing on the top. So, and you get the same number. So you've got like 3 different ways or more to work this thing out. Anyway, you get and you can go on the moon and do measurements and same measurements. There'll be different numbers, but the ratios will be the same, and you'll come up with that same thing. So this gives you the effect of mass density has on the curvature for any kind of mass all over the universe. Absolutely amazing little tiny constant. Okay, so we have now a match for both the numerical value and the units. And could these units be related to curvature? Oh, darn right. So let's go and see what Einstein said. And I took this out of his book. My book's almost falling apart. Funny, while I'm looking to find this sucker. Oh, there it is. Yeah, I read this book earlier, and I understood the first part. This was like 40 years ago or something. And then I read the last part, and it's like they had these ugly little symbols, like like this. I can't get rid of my fingers, but if I could. Anyway, it's like an F with a little hook on it. It's like one of those needles that one time I actually cut my leg open. I jumped on a stone wall, and the wall fell down on me and cut me to the bone. I didn't want to look at it. I just ran and ran and ran. And then I wasn't planning on talking about this, but that little hook reminded me. So I ran. I knew I was badly injured, and I didn't want to face up to it, so I just continued running. And I was wearing a long Adidas shorts, so I didn't have to look at it. And then at some point, I gained the courage, and I pulled up I was a teenager, and I pulled up my Adidas long pants, and saw that my shin was cut right to the bone by the rock. And so I ran. I was in Canada, let me tell you. So I ran to it was Kingston General Hospital, and I just went right in there and told the doctor, pointed to it, and he said, oh, I'll stitch you up. I said, great. So he stitched me up and he says, do you want any, anything for the pain? And I laughed, I'm like in Arabic, they say, batul, I'm such a hero, And I thought it was. And so he stitched me up with this hooky needle. And and it was great. The pain doesn't bother me so much for little things like that. And so then at the end, the doctor's finished, and I was curious. I thought, oh, doctor, can you show me your needle? I'm interested because I've done a lot of sewing myself. Can you show me the needle there? And I was expecting a long one, like a sailcloth needle. But he pulls out this little kind of F-shaped needle with a hook on it. And I took one look at it, and phew, I fainted. So I woke up a while later. I didn't know what happened. I was all sweaty, clammy, and the doctor's laughing his head off, such a hero. And I see this little needle, and I faint immediately. Well, anyway, I look in Einstein's book, and in the latter half, it's just filled with all these little nasty-looking hook things. So when I looked at that, I almost, you almost faint when you look at that. And I didn't, they don't tell you in there what that little thing is. It turns out, well, I won't tell you. We're not going to talk about it in this series. But anyway, so what did Einstein find on this constant? And he found 1.86 times 10 to the minus 27. Now this book is the latest edition, 1955, the year before he died. And look, it should be 1.86 times 10 to the minus 26, and he still has 1.86 times 10 to the minus 27. This is Einstein, one of the best physicists we've ever known. And there's still little errors there, here and there. And this one he didn't catch. And so the point is, just relax. When you do new stuff, you got to make errors, and don't worry about it, but catch them by whatever means you can. Check the units, check the number. Go on the internet. If you know any people in physics, run it by them. Always a good thing. So we found that we got the same value after fixing up Einstein's version. Now we're going to calculate the total curvature associated with the mass density of the Earth. And I'll show you my drawing of what that looks like. Okay, notice that I will use 8 pi g over c squared when converting mass density to curvature, and I'll use 8 pi g to the fourth divided by c to the fourth when converting energy density to curvature. And that's because it works out the same thing. You just have to take into account the units. Because when you're talking about the curvature of the Earth, you don't give a hoot whether you talk about the Earth mass or the Earth energy. I mean, it's the same Earth and it has the same curvature. So you have to adjust for the units, because what the Earth does to space doesn't depend on whether you call what the Earth has, whether you call it having mass or whether you call it having energy, because it's the same darn thing, just two different names. So, so let's actually calculate that next. I'm going to move this thing up. So, it's playing with me. I'm not going to let it bug me. So we got that space-time calculated. So let's calculate this. I have the same picture again, but the curvature that the Earth imposes on space-time because of its mass density is not the curvature of the sphere of the Earth. No. So we just did this. We derived this constant 8 pi g over c squared equals 1.87 times 10 to the minus 26. We derived it a few different ways. And we have that's equal to the curvature divided by the mass density, which means that we can calculate the curvature is going to be that constant, 1.87 times 10 to the minus 26, times the mass density of the Earth. And we know that. The mass density of the Earth is 5,441.6 kilograms per meter cubed. So that's the mass density, which of course you can say the mass of the whole Earth is, and it has so many meters. cubed. But for 1 meter cubed, it weighs 5,441 pounds. Just something to keep in your pocket. So when I multiply that out, I get that the four-space curvature, space and time, is 1.87 times 10 to the minus 26 meters per kilogram. So you're thinking that the space-time curvature, you got the whole Earth and it's going to be a giant curvature. Well, it's 1.87 times 10 to the minus 26 meters per kilogram. It's actually quite tiny. And that at the times, I didn't even finish the multiplication, times 5,441.6 kilograms per meters cubed, and we get, this is better, 1.01542 times 10 to the minus 22, 1 over meter squared. So this is the curvature, this last number, 1.01542 times 10 to the minus 22. Again, that you're expecting something big and you get this small curvature. So the radius of the curve induced by the Earth's mass onto space-time is 9.92 times 10 to the 10 meters. That's the radius when you flip that. Let's see now, 1 over meter squared. Yeah, when you flip the 1.01542 times 10 to the minus 22, you get a number. But that's for meters squared. You want the radius, which is just meters, so you have to take the square root of that. And so quite predictably, the square root of 10 to the minus 2 is going to be something times 10 to the 10. So it all holds together here. So the radius of curvature induced by Earth mass onto space-time is 100 billion meters, a very long radius. Now, why I was saying it's such a small curve is because if you have a curvature, if you have a small radius, you get a tight curve, a lot of curvature. If you have a long radius, it seems almost straight. The curvature is so small. And this radius of curvature is 100 million kilometers long. It's 2/3 the distance from the Earth to the Sun. So it's almost the full distance, this radius that's sweeping out this arc. I'll do it this way, It's 2/3 the way to the Sun, and that long from the Earth to the Sun. A very straight kind of curve, which is why it's so hard to measure. So I'm going to show you that picture graphically so you can see. So here I got a picture of the Sun, and then I got a picture of the little Earth here. And I went roughly 2/3, and I made an arc. So that shows you the arc, and it looks pretty good. But let's pull it back to the Earth, because that arc represents the curvature that the Earth imposes on the space-time, surrounding space-time, close to the Earth. So I move that curve, where the curve is correct. Move that curve close to the Earth. Now the curve, when you get farther away from the Earth, the gravitational force gets less and less, so the curvature gets less and less. This is the curvature at the Earth's surface. So I drew a straight line here without any dashes, and then I showed here the light from grazing light, path of grazing light coming close to the Earth. It comes in at this angle, and then gets curved in the vicinity of the Earth. And then it comes out and starts going straighter and straighter and straighter. And then it's going straight through space-time again, away from the Earth. And you get that path of grazing light, which looks pretty darn straight. And when you measure it, it's very, very difficult to even detect that curvature on the Earth's surface. Which is why astronomers like to use eclipses of the Sun and see how much the Sun deflects stars, because the Sun's gravity, the Sun's mass density, the mass is so large, and the mass density is probably low, but the total mass is large and the total curvature is effect. The distances traveled are long enough to get the curve to do, and it's so close. So it's they prefer that method to measuring on the Earth, which is very difficult. So we're getting close here. So I want to do a summary here of the things we've covered. We covered how to calculate the curvature using parallel transport, and that'll be useful. We also talked about earlier, and by the way, I'm not finished totally this presentation because I'm going to next build the stress energy tensor, which Einstein's gravitational field equation. I'm going to build it up, and we have the units. But I just want to give a little bit of summary of some of the things we've found so far. And we had the sphere over on the far left, the sphere of dust particles or sand, and the Earth moving through time, and we see in that direction the sphere coming together, which is you can figure that out as the strain acceleration. Remember, I showed the actual equivalence between stress and strain acceleration. The strain is the compression, and those little glass. Well, glass is what sand is. A spherical shell of sand is undergoing an acceleration, strain acceleration. So the stress and the strain acceleration are equivalent to the curvature and the mass density. So you can remember, talk two languages. Here's where we can use that. And yeah, we found out that the geometric curvature of a sphere is 1 over r squared. And we also went through the Lorentz Transformation, actually derived it and showed a picture of it. And we worked out that the 8 pi g over c squared is equal to the curvature divided by the mass density. And so what's in effect, we're ready. We've got the pieces now to be able to put the Einstein stress energy field equation together using these components. And if we just check to make sure that the physics is correct, we'll get the complete theory without having to get into this elaborate mathematics. We'll run, in due time, we will run into the mathematics, and I'll give you a taste of that without forcing you to do any of it. But I'll just show you a little picture of it in the next presentation. And with that, I'm getting ready to sign off here. The next presentation will be General Relativity with the headlights on. I use images so you can see what's going on. You're not floundering around in the dark. And that'll be video number 4. I'm looking forward to that. And again, thank you very much. I really enjoyed presenting this. It was a lot of fun and actually a thrill. And I look forward to meeting with you again in this video number 4. So, thank you. Signing off.